Okay, so today, as I wrote you by email, there will be one of the groups of last year. We give the presentation of their project at the end of this lesson, so you start getting a feeling of what is the project about. So meanwhile, while we are waiting for them, let's go on with the binary trie methods. We have seen the basic disjoint prefix binary trie. Do you have questions until now? So now we have seen the basic binary trie, the complete binary trie, and the disjoint prefix. Now we can go on and look at the path compressed trie, which is another method to optimize the basic structure. And the principle is that in a compressed trie, non-gray nodes that have only one child, so the white nodes with a single link coming out of them, can be removed, and so long chains of white nodes can be compressed into a single node. These chains of white nodes are also called one-way branches because they correspond to a single path where you don't have any bifurcation. So it's possible to compress them in a single node, but in order to avoid losing information about the path, we have to include in this node two extra variables. One is called skip, which indicates how many bits have been skipped, compressed on the path, and the other one is segment, that is the original value of that sequence of bits, so the original stream of bits that have been compressed. So let's start from the node, from the original binary trie that you see on the left. And let me put this in. Okay. The first step is finding in the original binary trie the chains of white nodes, or better, those white nodes which have a single child. For instance, if you look at the top of the binary trie on the left, there is already a chain. Let me see if I can show the pointer. So here you notice that there is a chain, a white node with a single child. So we can remove it and reduce the number of nodes by one. When we introduce this compression, you have also always to consider that there is when you remove a white node, then you are also removing, compressing the link that that comes out of that white node. So in this case, we remove one node, so the skip variable would be 1. And the segment variable, that is the value of the original bit on the path, along the path that has been removed, will be 0, which is the bit, the value of the bit corresponding to this arc below. So you remove the node and you also remove the arc below. And this means that the node that was attached to the node, the arc that is being removed will be attached to the original arc above the node that has been removed. So P3, basically this gray node P3, will be directly attached to this arc which is surviving, and that is 0. And in P3 you have to add these two extra fields, the skip value and the segment value. Skip will be 1, segment will be 0. Okay. So we can now move on to find other cases of white nodes with a single child. Here there is another one. So you can remove this white node here, and the arc that comes down from that white node. In this case, the skip value is again 1, segment is 1 because this arc was labeled with 1. Okay. And the node P5 will be attached to the remaining, to the surviving arc, that is the one that comes out from P2. We can move on. Here is another example, the same as before. Okay, so again, skip 1, segment 0. And then here we have an example of a chain of 2 white nodes that can be removed. So we can remove the bottom one with the connected arc, and then also the other one on the top with the connected arc. And therefore skip value would be 2, segment is 1, 1, because it's these two are the labels of the nodes, of the arcs, this and this one, that were removed. There is a final possibility here, again another white node with a single child, and again we can compress the branch and with the skip 1, segment 1. Okay. So what happens when we perform this, we use this compressed tree in order to make lookup operation. So this is on the left side you have the lookup into the original uncompressed trie, and here you have the lookup corresponding to lookup in the compressed trie. When we trace the path along the compressed trie, we have of course to take into account the skip and the segment fields whenever we are crossing a node with compression. So if you start with this destination address, that is the example, the first 2 bits does not require any special care because we are moving on the original, like on the original trie. So this movement corresponds to arriving in the original trie to this white node. Okay. But here we arrive to a gray node that has been compressed. Okay. So we have a skip and a segment. So in order to continue the path, we have now to take a number of bits in the destination address, further bits in the destination address, in the number that is indicated by the skip, in this case only 1. Consider the value and see if the value of this sequence of bits is matching the value of the segment field. Okay. In this case, the next bit is a 1, so it is matching the value of the segment. If we have a matching, we can go on. So we can start crossing this compressed node. You can visualize this as we have the permission to enter into the compressed node. Okay. So once we have entered the compressed node, then we can continue to trace the path. So then we have a 0, we go here, and the 1, and finally we get to P7. Okay. P7 is the solution, and it's exactly the same solution that you find, of course, in the original uncompressed binary trie. Let's look at another example. This is another destination address. So again, we take the first 2 bits, and this is a normal path because we don't have any compression. We arrive to this gray node again, which is a compressed node, so we have to consider one further bit because skip is equal to 1. The value of the bit is 1. We have to match it against the value of segment, which is 1. There is a match, so we have permission to enter this node. After entering the node, we can go on because we have a 0 here and then another 0. And so we land on another compressed node. Skip is equal to 1, so we have to consider the further bit in the destination address. Segment is equal to 1, but the next bit is equal to 0, so we don't have match. So in this case, we cannot enter this node, the P8, so we have to bounce back. And as in a normal search on a binary trie, we have to backtrack to the last gray node that was encountered. So in this case, P5. Okay. So the final result is P5, and is the same that you obtain here in the uncompressed tree. But in the uncompressed tree, the path that you have to travel in order to reach the point of return, let's say, is longer than in the compressed tree. Okay. What is the complexity in this case? The lookup complexity doesn't change compared to the original binary trie. It's always W in the worst case, but the storage complexity is decreased by a factor of W, and basically the highest advantage is gained when you have a lot of long chains of white node. Storage complexity N refers to the case when you, by compressing everything, you create a complete trie, where all the gray nodes are at the bottom, and therefore, since you have n nodes, you have n entries in the routing table. It means that you will have n gray nodes. If they are at the bottom, it means that you built a tree of key levels, where key is the logarithm base 2 of n. So n is equal to 2 rise to the key. So, for example, in this case, you have 8 nodes, n is equal to 8, and therefore you have a tree with 3 levels. And as you know from the properties of the finite sum of 2 to the key in several stages, the total number of nodes is n minus 1. Okay. So this is the binary tree with the lowest possible redundancy, because of course those nodes, those white nodes that are surviving, cannot be compressed because each of them has 2 children. That's the minimum you can have in order to connect all the n nodes, the n gray nodes. We can compare this complexity evaluation with the previous complexity evaluation in terms of storage requirement that we saw with the standard binary trie. And basically this is the path compressed version with a total of n nodes, as we have already said. And you can see that there are the n gray nodes at the bottom. The uncompressed version, in the worst case, would be like that, where you have all the prefixes with length w, but actually the gray nodes are all at the bottom. Okay? And so the difference between the two complexity values is exactly given by the fact that when you compress everything, if you start from the scheme that we have introduced to justify the complexity of the uncompressed binary node and binary tree, and you compress everything, then you go back to this situation here. So you remove the rectangle of the big rectangle of white nodes. Okay, so it's quite understandable. Okay. This concept of path compression is actually not limited to the application of IP address lookup. It was invented earlier, especially to represent text in an efficient way. And this is the generalization is called the Radix tree. In the Radix tree, each node that has only a child is merged with its parents, and so if you use this representation to represent text, after compression, before compression, you have that each R is labeled with a single letter. After compression, you can label the arcs with sequences of letters. This is the most famous example. So if you have all these words that are in a list and have common parts, the beginning of the word is in common, then you can use this kind of Radix tree in order to compress them in an efficient way. And this is it's a structure that is very much used in the spell checkers. Okay, the spell checkers work with that structure. In fact, if you notice, if you write a word, for example, with Microsoft Word spell checker, and you make a mistake in the last letters, so at the end of the word, then the spell checker will correct it. In most cases, in the right way. If you make a mistake at the beginning of the word, in the first letters, usually it is not able to correct it because in the first letters you have a single path, so you don't have alternatives. And so you are completely unmatching the entire tree. But instead, if you are making if you are missing other words, then it is able to find the correction in an easy way because of this tree representation. And in particular, this Radix trie, in case the Radix is the maximum number of branches that you can start from a node, so the maximum number of arcs that exit a node, or the maximum number of children. If this value is 2, the tree is called Patricia. Patricia is an acronym, actually means practical algorithm to retrieve information coded in alphanumeric, but it's a very nice acronym, it's a nice name, and it was introduced back in '68 by Morrison. Okay. So now let's go to another variation of the binary tree, which is called multibit trie. In the multibit trie, we can improve the lookup performance by using nodes that represent not a single bits, but set of bits or string of bits. So we can traverse multi-bits with a single memory access. And each subtrie that is represented by these compressed nodes must hold the informations of the next hop information of each entry that belongs to that subtrie, plus also the pointers to the other nodes of this multi-bit structure. And the parameter stride or lookup stride is the number of bits that are compressed in a single node. So, for example, if the lookup stride is 3, it means that each node in the trie actually represent a sequence of 3 bits. Okay, so it must have 8 entries. That in order to hold the content in terms of next hop information, and also 8 entries in order to hold the pointers to possible other nodes in the tree that are reachable from that node. This improves the lookup performance, because we can do the lookup operation faster, but it requires a larger memory. Why the memory is expanded? The reason is that each of these nodes that are actually corresponding to a subtrie represent these subtries as complete tries. So you have first to transform the original graph into a set of small subcomplete tries, and then map these subcomplete tries into these nodes. So let's look again at, as usual, at an example, because with the example you can understand better. So in this case, you have to. My voice is going. So in this case, you have to start with. We start always with the prefix database. We start with the original trie that you see, and we decide a priori that the stride is equal to 3. So this means that we will group the bits of the incoming address, of the incoming destination address of the packet in groups of 3 bits. And therefore we can also divide the prefix database into subsets according to the length of the prefixes. So we have first on the top all the prefixes that have a length equal or less to 3. They will be all represented into the first node having a stride of 3. Then, in order to represent all the prefixes of length that is equal or less than 6, they fall into the category. The next category for again with the stride equal to 3. So we will need other nodes to represent that set of prefixes. And here in this case we have also one prefix that is longer than 6. We will need other nodes also for that node, for that prefix. So let's start with the first stride. The first stride corresponds to that set of prefix entries from P1 to P5, and it also corresponds to this part of the original trie that basically takes 3 levels of the original trie. We have to map it onto a node of this multi-trie representation. So it means first that we have to take this subtrie and transform it into a complete subtrie. Okay, so we have to do all the same procedure that we did to build a complete trie. So you take the entries, the gray nodes that are already in the bottom. This is the bottom level. So P4 and P5, they have a length equal to 3, so they will stay in the same position here and here in the complete trie. Then we go up one level. In one level, the upper level, we find P3, which is here and here. P3 must be pushed down, and so the 2 copies of P3 will stay in the first 2 nodes. One level up, we have P2, that is this one here. P2 has to be pushed down, so here P4 and P5 are already occupied, so you have to copy P2 in this position and this position. And finally P1, which is at the top, that will be copied in the 2 remaining empty nodes at the bottom. And so at the end you have this is the complete trie that corresponds to the first part. Okay. Then let's now move to the second level. So we have another stride, and you can see that once we are in this set of prefixes, this prefix P6 is attached to one node of the previous trie, so it is along a first branch. So we have to take the subtrie that is connected to this branch. In this case, the subtrie is this one. Okay. So it's P6 and then two other white nodes, and it corresponds to the next stride because you can see that there are 3 bits, 0, 0, and 1. This must be mapped on another complete binary trie of depth 3, okay, equal to the stride. Here we have only one gray node that is P6. P6 must be pushed down, so you have 4 replica of P6 in the bottom position. Now we go on. There is this remaining subset of prefixes that corresponds to this branch attached to another node of the first subtrie. So it means that you need another subtrie to represent it. So we have to create again the tree that is done like that, and repeat the procedure. In this case, P8 is already in the correct position. P7 that is here, so in this position here, must be pushed down, so you have this entry. Okay. Then we have something more, another stride, P8, P9. P9 corresponds to this node, which is connected to one node of this subtrie here. And it contains only P9, but still you have to represent it as a complete binary trie of depth 3 according to the stride, and so P9 is pushed down in this way. Notice that we have then to consider also the connections, the links or the pointers to connect the macro nodes that we have created. So this is connected to this one and to this one, and you have also to consider where these links land on one side and on the other. So this link here land on this node of the first trie. These other links land on this other node, and so on. Okay. So this is the preliminary transformation. Now we can start transforming the data structure, or creating the data structure that can be then used to store this tree. So since here we have to represent a subtrie with by a single node, we need in the node not just one information field and two pointers like in the binary trie, but we need one array of information fields and one array of pointers. Okay? The number of positions in these two arrays is equal to 2 to the stride. In this case, stride is 3, so you need 8 positions for the information and 8 positions for the pointers. And this is the data structure that corresponds to what we have built. So here again you have the prefix database that is divided according to the stride, and you have simply to take the result, the outcome of this operation, reading only the bottom lines, the bottom set of nodes, and directly copying all the values into the arrays of the nodes. So you have in the first node here you have P3, P3, P1, P1, P2, P4, P2, and P5. Where basically P5 comes from directly from the entry, which is length 3, P4 as well. The two copies of P3 comes from the expansion of the prefix P3 that is of length 2. And then you have the expansion of P2, and then the projection of P1. And obviously all these entries can be accessed by the address that is written on the left side here, which corresponds to the sequence of bits that you have in the incoming IP destination address, which will lead to in the original type, which will lead with the path to touch that specific gray node. And then we have the pointers. So from this position in the first subtrie, there is the pointer to node number 1. This other position, there is the pointer to node number 2, and now you can start filling up the entries of node number 1. Here there are the 6 copies of P6, then there is 2 copies of P7 and P8, and finally in node number 1 you have the pointer to node number 3, which is the last piece of the original trie, where here you have the expansion and the projection of P9 forming 4 copies. Okay, so this is the rule. Now you can, as you can see, we have decreased a lot the number of nodes compared to the original trie. However, each node contains 2 arrays, so we have expanded the dimension of the node. Lookup example, it's very simple. Here is the destination address. Since here the stride is equal to 3, it means that you have to take the first 3 bits of the address and use them to look into the first node, that is the root node. And here is the position. So you will find P5 as the first matching prefix. But there is also a pointer, so you have to go down to continue. The pointer leads to node 2. In order to inspect node 2, you take the next 3 bits because the stride is equal to 3. In node 2, the 3 bits corresponds to the address 010, so it's P7. P7, here you don't have any other pointer, so the path is finished, and therefore P7 is the final answer. You don't have to consider further bits. Okay. So what is the complexity of this method? The lookup complexity is obviously W divided by key, where key is the stride. Because each time you look into a node, the complexity is the same as the complete binary tree complexity, which is O1. Okay. And now the number of nodes are W divided by key. The storage complexity is the number of nodes, in the worst case W divided by key, multiplied by N, which is the basic same complexity as the complete trie, but with less levels. But you have to take into account that each node contains an array, and the array is of 2 to the key positions, so you have to multiply NW divided by key by 2 to the key. Okay. And the update complexity also is quite similar, and similar to the update complexity of a complete trie, of a standard binary trie with less nodes, because now the levels are W divided by key. But each time you have to change something into a node, that is a complex structure, you have to go and access inside the memory an array of 2 to the key positions. So this is why there is this plus 2 to the rise to the key. Okay. Questions? So we have improved the lookup complexity, but we increased the memory. However, there is another improvement which allows to optimize this architecture and to reduce the requirement in terms of memory. And in particular, we can half the requirement in terms of memory by this technique. And this technique consists in using one single array instead of 2 in each node, and this array will contain next hop information in some positions and pointers in some other positions. Okay? So we are just compressing the information inside each node. However, in order to do this, we have still to maintain the correct representation of the paths into the the structure. So before compressing the two, colliding the two arrays into a single array, we have to perform an operation of leaf pushing again. And in particular, the information that should stay in the same position where you have a pointer has to be pushed down to the next node. and I'm going to show you how this is done. So let's start from the same example as before. We have already built on the architecture based on complete subtries. Now here you see, for example, that you have this link connecting P2 to these other subnode, and here you have the link connecting the pointer connecting P5 to these other subnode. Since when we are visiting P2, then we will have to continue and visit also this other node. Then we can transfer the information that originally is contained in P2 and push it down into the next node. Okay, so we just copy the content of P2, which was great, and by the same, always the same technique of leaf pushing, we copy it here in the free positions of the next node, and in doing this, we can turn this node to white. Then we do the same for P5. We copy the position here, and this becomes white. And we do the same also with P6. It is here. Copy the content, and this becomes gray. Okay. Now here, in this in the first node, you don't need to write anything in the array, so you can delete the content of the array of the next stops in corresponding to that node, and the same holds for this node. Okay. On the other hand, on the other side, you had the array of the pointers, and the array of the pointers had something only in these two nodes and nothing in the other nodes. So now you can merge the two arrays, and you don't have any collision. So this is the result. So when we start to create the first node, we have basically here the P3, P2, P1, and P1 again. And in the last position where there was P5, P5 is projected to the next node, so we can enter the pointer. And the same here, where we had originally P2, P2 is projected, so you can enter the pointer. And then here there was P6, but P6 is projected down, so you have space for the pointer, and that's all. Okay. So now the memory size is exactly the half of the previous case. So we have saved in memory. The lookup complexity is exactly the same, okay, because nothing changed. In fact, if you see, this is the same example of lookup operation. You start from here, 111. There was a P5 in origin. This is the uncompressed version. This is the compressed version. But in P5 you find, sorry, you are here. You find only the pointer, so you go down, and then in this case you start looking into node number 2 with the key 010, and there was P7, and here is the same. You start looking at node number 2, 010, you find P7. Okay. So if you had, for example, 111 and then let's say 000, you went down here, you find P5, and then you find P5 in this position. Okay. Any questions? The final improvement that we can see about the binary tries is the level compression trie, which is a technique basically to merge the two concepts of path compression and multibit trie compression. And the idea is that we can transform a path compressed trie into a multibit trie in order to optimize the structure. And the level compression is possible when you can compress an entire subtrie into a single node. So it is especially interesting when you have the possibility of combining level compression and multi-bit compression. Path compression is very effective when you have sparsely populated trees, and multi-bit compression is effective when you have densely populated trees. So level compression is the mixture of the two. So how can we perform this? Buongiorno. Buongiorno. They are the group. Okay. So just finish this and then I will leave the podium to them. So how can we perform level compression? First of all, we have to start with disjoint binary tree. So the first operation from the original binary tree is to push all the gray nodes at the bottom, not necessarily at the same level as you can see here, but all the gray nodes are in a leaf position. Okay, this is the first, preliminary starting point. Then we can perform the compression of all the paths. So the chains of white nodes can be compressed, as we have seen in the path compression technique. And the trick is to try to do this path compression so that you have at the beginning a subtree of nodes that are all white. Okay. So in this case, for example, you can compress here this chain. Okay. So you have skip 2 and segment 0, 1. Then there is another long chain here. You compress it. We have skip 3 and segment 0, 0, 0. Okay. In this particular example, we have only these two possibilities of doing path compression because, as you can see, all the other white nodes that are remaining have always two children, so you cannot do path compression anymore. But here you can see that we have a subtree that is completely of white nodes. So, since this subtree is completely of white nodes, we can transform it in a multi-bit node. Okay. And in this case, we have 3 levels, so we can transform it into a node with stride equal to 3 and skip equal to 0 because we are not doing any compression. Okay. So this will be mapped into an array, of course, of 8 positions, since we have 2 to the key, 2 to the stride positions. And this is the first node of the tree. Then you can notice that we have also here another subnode, another subtree which contains a small subtree of white nodes. So again, we can do level compression, and we can transform it into a node of stride 2 and skip 0. Now we can generalize this indication of a skip, stride, and segment to all the nodes. So we have, when we just have the multibit compression, we will have a certain stride and skip equal to 0. When we have instead a compression, we have like in this case, stride equal to 1 but skip equal to 3, and of course we have to put also the segment. All the other gray nodes can be associated to skip equal to 0 and stride equal to 0. So this is the transformation, and then you can try to do some lookup operations, like in this case. So here, for example, you have 1, 1, 1, 0, 0, 0. This is the path of the original trie, and this is the path on the compressed, level compressed version. You take the first 3 bits, 1, 1, 1, to go here, then the other 3 bits, 0, 0, 0, to go into this node. That is stride 1 but skip equal to 3. So you have to check matching of the next 3 bits with the segment, and they are matching. Okay, so you can cross this node and arrive to node 13. This is basically what they say. So this is the successful operation. This is another case, 1, 1, 1, 0, 1, 0, 0. Again, you use the first 3 bits to move into the first node, and you get here again. Then you have 0, 1, 0, but here you have an unsuccessful matching because it is not matching with the segment. So in this case, you don't have any matching in this tree for this particular destination address. Okay. Here the default router is not configured because the root is white. If you want to have in any case a positive matching, you can configure the white node, the root node, and turn it into a gray node. And so in this case, you can keep into account and say that if you have a successful matching and you have to backtrack to the root, then you find the solution. Okay. The complexity in this case is very similar to the multibit trie complexity, and that, of course, in this case you cannot predict the stride in advance. So this is only an indication when you assume that you have a stride always equal to t, but that is not necessarily constant. Okay, so I stop, and they can continue to with the presentation of the project. So if you want to come here with the PC.